Szczepańczyk. Dr. Szczepańczyk was our student in Warsaw. He did here his bachelor with Andrzej Okołów and his master degree with Marek Professor Demiański. Now he is for a long time in the University of Florida in Gainesville, as far as I understand. And he's working on gravitational waves. So he is doing this other side of general relativity. And the title of the talk, Multi-Messenger Astrophysics with Gravitational Wave Sources Preparing for the Unexpected. Marek, the microphone is yours.
Thank you very much for this introduction. Thank you very much for this opportunity to talk at this seminar and showing my research. So my research is on multi-messenger astrophysics with gravitational wave sources, and we are most interested in preparing for the unexpected gravitational waves. And I divided my talk into two parts. First one, I will talk in general, what is the significance of this area of research in broad science, and then the overview of this area and the future prospects. In the second part, I will talk about gravitational wave searches, gravitational wave detections, specifically the very first gravitational wave from 2015, and an intermediate mass black hole back in 2019. I will talk about the gravitational wave transient catalogs, potential sources like core collapse supernovae, and the generic searches. So let me start from with the first part, and let me talk about the importance, the role of astrophysics in the discovery. And I chose it by showing a graph of a timeline of Nobel prizes across the last century, where we have where the different fields are divided: condensed matter, atomic molecular physics, nuclear physics, and so on. So certain fields were awarded fairly uniformly across the last century, like condensed matter, atomic physics, or particle physics. But there is a very interesting trend for astronomy, astrophysics, and cosmology. So for a long time, the Nobel prizes were really, really rare. But in the last decade, just in the last decade, there were several Nobel prizes. So in total, we have around 15 of them for astronomy, astrophysics, and cosmology. And in the last decade, just in the last decade, we had 7 of them, where 4 of them are linked to general relativity, detection of gravitational wave, developments in theoretical cosmology, observation of supermassive black hole in center of Milky Way, black holes as a consequences of general relativity for Roger Penrose. Then we have 3 awards for using astronomical data, expansion of the universe, neutrino oscillations, and exoplanets. So there is a very it's a really great trend for astronomy and astrophysics, and with bigger detectors, with larger surveys, with detecting more and more gravitational wave sources. This trend will continue, and astronomy, astrophysics, cosmology will continue to be more and more relevant in physics. Now, within astronomy and astrophysics, if we look at the decadal survey for 2020s, for this decade, the committee chose 3 broad themes. First one is new messengers and new physics that explores energetic processes like colliding black holes, nature of dark matter, dark energy. Then, in a smaller scale, worlds and suns into context. So, exoplanets, evolution of stars, potential habitable solar systems, and then finally, cosmic ecosystems, linking observation and modeling of stars, galaxies, gas, trying to find the link to galaxy growth. And within in these broad themes, there are priority areas that are highlighted. And for the new messengers and new physics, we have new windows on the dynamic universe. And my research fits here very, very well. We try to understand the dynamic of universe with colliding black holes and many other sources that I'll describe, using new windows, new messengers, primarily for me gravitational waves, but also electromagnetic waves and other messengers. And I will talk more about different messengers and
But could you explain the meaning of the word new messenger? What do you mean by this?
Yes. So a messenger is a distinctive distinctive signal that carries unique information about the source. And I will talk more maybe later.
Gravitational wave.
So we have gravitational waves, electromagnetic waves, cosmic rays, and neutrinos. And maybe I can, I have a special slide where I described all of them in more in details. So maybe I can wait with full answer to later, if this is okay.
Go ahead.
Okay, so now let me give an intuitive overview between a comparison between conventional and gravitational wave astronomy. Conventional astronomy uses electromagnetic waves like visible light, X-ray, microwave, and so on. Also cosmic rays and neutrinos and some other particles. And in an intuitive sense, we are looking at the universe with our eyes. We just stare at the sky. In the gravitational wave astronomy, we observe the universe using gravitational waves. These are ripples of space-time, oscillation of the space-time itself. So we can plug them. So we are using detectors that can be understood like microphones, and we can plug them to the speakers, and we can, in a sense, listen to the universe. So this is like an intuitive overview. Now, the very foundation of gravitational wave astronomy is Einstein Equation. It's a beautiful equation that connects the curvature of space-time with mass energy distribution. And as Wheeler is saying, space-time tells matter how to move, and matter tells space-time how to curve. And we can look at Einstein equation in two ways. We can solve it analytically, numerically, and this is what people are doing, especially the department in Warsaw was doing for decades. And as Professor Lewandowski said at the beginning, we can also look at this in a different way. So let the nature solve it for us. We have an abundance. We have many gravitational wave sources. Some of them are detected. Some of them are waiting discovery, but only few of them are precisely modeled. So when we observe the universe as it is, we can have solutions coming from some very interesting sources. Now, talking about sources, in order to generate gravitational waves, we need to use quadrupole formula, and the gravitational wave strain is proportional to the second time derivative of a quadrupole moment. Intuitively, we need some spherical mass energy movement. So if we have a star that is ideally spherical, even if it is rotating, it does not emit gravitational waves. We need to have like mountain of the star, we need to do some deformation. And when we think about aspherical symmetrical sources, like systems, and the most efficient are compact binaries. Binaries with circular or elliptical orbit, black holes with neutron stars, binary neutron stars, very heavy black holes with a hyperbolic encounters, head-on collision of black holes, like different spins of black holes, different mass ratio, and so on. The list is long. Now, we also can have generation of gravitational waves with other astrophysical sources like Park Club supernova, neutron star or pulsar glitches, or even cosmic strings. To detect gravitational waves, we use interferometers, but let me explain the basic principle. Let's imagine we have two objects that are at a distance L, and when the gravitational wave is passing through them, they start changing distance of delta L, and what we measure is the strain that is simply delta L over L. So the longer, the more far away are the objects, the larger, the smaller strain we can detect. And for the real detection, we use gravitational wave interferometers that are made from three basic components: a beam splitter in the center, and then two arms with mirrors at the end. We send a laser light into the beam splitter where the beam is split 50-50. The light is traveling all the way to the end to the mirrors, and it reflects back and then recombines in the photodiode. And by design, the photodiode is kept with the destructive interference in a dark mode. When the gravitational wave is passing from any source, the length of the arms are changing, and light appears in the photodiode. And the longer interferometers, the more sensitive they are. And the current detectors are 4 kilometers long in LIGO detectors in US, and then 3 kilometers long back in Europe, the Virgo detectors. Here I show an example, the aerial view of the Hanford detector. And as a PhD student, I was working. I spent half a year in Hanford, and I was working on the instrument. And I'm one of the few people who are allowed to go to the chamber to work close to the test mass, close to the mirror inside the vacuum chamber. And here I show a picture of me with this marvel of engineering with the test mass mirror. So the gravitational waves are very weak, and the detectors are so sensitive that they are disturbed by
Excuse
many.
me, may I
Yep.
ask a question about this measurement? Because as far as I've heard from some people, if there is no signal, if there is no gravitational wave, then you have black point roughly, phase zero. And
That's
then
correct.
suddenly signal comes and the phase is no longer zero, it oscillates, whatever. but the measurement is that you follow with mirrors this phase in such a way that you have always black point. So the measurement is the movement of mirrors. Is it true?
So this is a simplified
Measurement of the signal, the measurement of the phase in time. It's just the motion of the mirrors, which cancel the phase.
Yes. So I described the basic working of an interferometer. In the real case, the mirrors are kept in one position. So wherever the light appear, there are feedback loops that takes back the mirrors to keep them in one position. And what we actually measure, is the whole complicated methodology, machinery to extract the strain. The force that is acting on the mirrors is translated into gravitational wave strain. So the dark part is kept to be dark all the time, and the strain is coming basically from the force acted by when the gravitational wave is passing. There's a certain force, and this force is balanced by feedback loops. I don't know if this is more clear.
Yes, I wanted to this confirmation. Thank you.
Yes, and if even if you have a very galactic source when the strain is gigantic, the feedback loops will the amplitudes can separate the mirrors a lot, but feedback loops will keep it in one place, so they will not start swinging in back and forth. Okay, thank you for the question. Yeah, please interrupt me when something when there's a need to clarification. So the gravitational wave detectors are so sensitive. They are so vulnerable to any disturbances from humans, from space, from Earth movements. In order to be sure that what we detect is gravitational wave, we need to compare them between different detectors that are spatially separated. And currently, we have LIGO, Hanford, and Livingstone, 2 detectors in US, and Virgo detector in Europe. Just in the last observing run, the Japanese detector Kagra joined the network, and GEO is another detector that is a testing technology detector, but also can observe the sky. And we have the detector in India that is currently under construction. In a few years, we'll start either observing or doing the first runs, depending on the progress. So here, let me go back to the previous question about about the messengers. So these are signals that carry unique information about a source. We look at the source from different angles, and there are 4 distinctive messengers. Gravitational waves are telling us about the dynamics of the source, the distribution of mass. Electromagnetic waves tell us about emission processes, the environment of a system, the temperature, the densities. Then we have neutrinos that are created in hadronic nuclear processes. It tells us about mainly thermodynamics. And then we have cosmic rays, very highly energetic particles that are created through nucleosynthesis, and there are unknown acceleration processes. So if we take 3 gravitational wave sources.
What are these cosmic rays? What are these high energy particles?
So it's like alpha particles, for example. This I think the most popular, most common. And and the cosmic rays are interesting because some of them are charged, and then we cannot really find where they are coming from what source. So this is like something challenging. But if we think about binary black holes, we already observed gravitational waves. We have potential candidates for electromagnetic radiation, which I will talk about that later. Binary neutron stars, we detected gravitational waves. We detected electromagnetic radiation. We haven't seen yet neutrinos nor cosmic rays. Corpulab supernova. These are exploding stars, and I will talk more about their mechanism. They are all of them are detected through electromagnetic radiation. We found there's one supernova where we observed neutrinos. We want to detect gravitational waves, and possibly there are models possibilities that there are cosmic rays coming from them as well.
Question, because usually these sources are very distant. So do you really think you can detect cosmic rays and neutrinos, even for these very distant sources? Expect that you will be able to detect them.
We already detected neutrinos for supernova from 1987 from Large Magellan Cloud. This is like 50 kiloparsecs, a dwarf galaxy like outside Milky Way. The challenge with neutrinos is that the flux is decaying like 1 over distance square. So the decay is pretty strong. So we need to have rather closer system. Another multi-messenger source that where we detected high energy neutrinos was with IceCube. There is a blazar, a supermassive black hole that basically is emitting a huge amount of energy, and over there, this is like I think a year or two, like some a pretty recent discovery. High energy neutrinos that were identified from that blazar. So this is like another. So that it's possible, but it's really hard. And the gravitational wave decay like 1 over distance. So they are a little bit easier to detect. I don't know if it helps.
Please continue. Yes, continue.
Okay, perfect.
Yes, you have answered. Thank you, because I understand that the process is very rare. Continue.
Okay, and to the end, to enter this the first part, let me talk about the future of the multi-messenger gravitational wave astrophysics. So currently we have around 90 gravitational wave detected, and the number will grow rapidly in the future. And I will talk more about the numbers in the next part. And all of this amount of gravitational waves will allow us explore the nuclear accretion state of dense matter, hopefully discover chromodynamics phase transition, measure the cosmological parameters, study black holes, test general relativity, maybe understand they will allow us to understand the nature of exploding stars, learn about dense stellar environments, about active galactic nuclei, and many, many more. We think that the future discoveries of gravitational waves from unexpected sources might play the key role in this exploration of the universe. And for the unexpected or surprising events, I mean basically gravitational waves coming from sources with exceptional properties, new gravitational wave sources, or those that have a challenging astrophysical models. So let me now get closer on how we search for gravitational wave sources, more or less on the research that I'm conducting. So there are two main methods to search for gravitational wave sources. First one is template-based or model-dependent methods, when we can calculate from general relativity gravitational wave waveforms very precisely, and we have binary black holes, binary systems with neutron stars. Then we have template-independent or model-independent, or also some people will say burst methods. So when we don't know what we're exactly searching for, the signal can be stochastic, can be non-deterministic. We don't have proper models, and for example, we have explosions like core collapse supernova. We may have cosmic strings, or some binaries with special properties, heavy, eccentric, with high spins, highly processing, and so on. Then there are two ways of how quickly we search. The first one is in low latency. So this is a rapid, within, think like seconds to minutes, identification of a gravitational wave. And this is crucial for astronomical follow-up. And then offline analysis, when we collected data, we look at the noise sources, and the analysis can last weeks or even years. So for the first method, the model-dependent searches, we calculate gravitational waves from general relativity, and we correlate it with detector data. These waveforms are called templates. So we, as on the image on the in the slide, we have in black a template, and then in red we have data, and we slide this template across the data. And when we match with the gravitational wave, the gravitational wave that is in the data, then the cross correlation achieves a maximum. So this is an optimal way to search for gravitational waves where we know exactly what we are searching for, namely like binary black holes from like binary black holes or binary systems within certain mass range, with certain parameter space. And this is something optimal mathematically when we have Gaussian noise. However, the gravitational wave data is not Gaussian. There's always something, some glitches, some certain noise. It's a very complicated detector with many complications in the data that the assumption of Gaussianity doesn't always hold. And you'll see later soon what are these challenges. And there are a few algorithms that do it, the match filtering pipelines. Now, the second method, the model independent. So we are not constrained to any model derived from general relativity. The prime tool is coherent wave burst, that is software designed to detect a wide range of gravitational wave transients without assuming any prior knowledge or assuming certain minimal assumption. So if you have binary black holes, when the binary is merging, the frequency of gravitational wave signal is growing over time, and doesn't matter what is the environment around, whether these are black holes or maybe some other objects. We have Newtonian gravity valid or general relativity or some deviations from general relativity. If we have two masses that collide, the frequency will grow. So these are very, very simple assumptions.
Typical value of this frequency. What is the typical value of this frequency?
It's the typical values are up to, those that we detect is up to like 300, 400 hertz. The lightest the lightest system, the binary neutron stars that we detected, the frequency was going up to 500 hertz, but typically it's like 200, 300 hertz for typical gravitational, typical peak frequencies. So this this algorithm detected the very first gravitational wave back in 2015, then detected the heaviest binary with first and second observing run data, and recently an intermediate mass binary black hole, and it detects gravitational waves together with model-dependent template-based searches. And during the last observing run, if we would have galactic supernova or any or cosmic string or anything that is non-standard, then that was the only algorithm that could have detected it. And I will talk about this more because I was in charge of this. I'm in charge of a lot of unmodeled analysis. So how does it work? We take data strain x of t. We transform it with an wavelet transform each detectors, and here on this image I show 3 detectors. We basically add the time frequency evolution together. The signal is now the gravitational wave signal is enhanced positively, but the noise destructively. So we identify events or excess power in this time frequency maps that are above the average noise. We select clusters, so we perform certain mathematical operations, and then with this event, we perform the inverse wavelet transform to get the waveform in time domain or in frequency domain. So below I show an example of gravitational wave from collapsing star. This is non-deterministic signal. We cannot have templates for this type of gravitational waves, and these model-independent methods are the only methods to be able to detect this type of sources. Mm-hmm. And on the right is a Fourier transform of this signal. So when the signal is strong, so signal to noise ratio in this case is 40, which is a very, very strong signal. Majority of the signal is reconstructed. Red is the reconstructed signal, and in black the signal that we added to the detector. Now, the low latency searches identify events rapidly, quickly. In the previous observing run, number 3, the model independent searches were performed only by coherent waivers, and we had we searched for generic burst transients, a gravitational wave with unknown morphology, or if you have an exploding star in our galaxy, then specially tuned searches that use minimal assumptions for stellar mass black holes up to around 100, and then intermediate mass black holes. And I will talk more about intermediate mass black holes later. And I will just say here that this search was discovered the very first intermediate mass black hole, and during 03, I was leading these searches. I was in charge of them running in the real time. 56 gravitational waves were identified during the whole observing run for the whole year of the run, and then half of them were identified by coherent wave burst. We had one potential burst transient signal that was not coming from a typical source. It was not identified by any match filtering model dependent searches, and it was sent automatically to the astronomers, and there was like many follow-ups with neutrino, X-ray, and other follow-up observations, and no coincidence were found. For the next observing run, and this will start in March next year, so literally within the next few months, we significantly improved the sensitivity of our algorithms to all sorts of potential gravitational wave signals. When in 03 we had a detection rate of 1 per week, this time we have a detection rate of 1 per day. So like every day there will be some gravitational wave, and it's a great opportunity for these discoveries. And the subthreshold events that we are detecting before gives
the reason
us
that you expect detection one day is because you increase the sensitivity, or you increase the number of detectors?
We increase sensitivity, and when we increase the sensitivity, we are gathering larger volume of space. So if we the volume of space goes like a cube of a distance, so it's worth to improve sensitivity even like 30–50%. Then we have more and more volume that we are gathering gravitational waves from. So if we improve, well, when we improve someday the sensitivity of 10 times, then we'll have 10 to 3 1,000 more gravitational waves. So yeah, this is the main reason, like gathering larger and larger volumes. Okay, so let me start. Let me talk about the very first gravitational wave observation. This was discovered back in 2015, and the solar and the masses of the black holes were around 30 solar masses each. Because astronomically, astronomers didn't observe very heavy black holes. They observed only up to like 10–15 solar masses. The match filtering, the model-dependent searches looked for binaries only up to around 15 solar masses. It's to lower the computation and be more efficient. However, Belczynski with others back in 2010 predicted existence of heavy black holes, like and and they found that, yeah, most likely we'll find a system of 30 solar masses, and this was our first gravitational wave detection. So on one side, many people didn't expect it, but it was predicted by Belczynski et al. Now for the detection, because the model independent searches use these weak assumptions. So whatever is the system, when the whatever is the system, it's easier for it to detect when the signal is stronger. And coherent waves detected this event in low latency as the only one. 3 minutes after gravitational wave arrived to the detector. And this is the very first gravitational wave detection from an object that is very compact, very energetic, and this is incredibly great laboratory for testing various theories. And here I just give an example from an overview from UN's 2016. This and other event constrained many emission mechanism beyond general relativity, like constraint having more dimensions, time varying gravitational constant, then constraint modification of gravitational wave propagation due to the Lorentz violation, mass of graviton. It allows testing the carrier geometry, and if we have, there was also a fairly coincident signal from gamma ray monitors, and if this is a real one, then we can have even more constraints. And what I want to highlight is a study of an event horizon.
What is the Kerr hypothesis?
So actually, I will explain it here, right here.
Very good, very good.
So when two black holes collide, the final black hole goes through the rotates and is perturbed, and these perturbations die exponentially, and there are certain resonances that depends only on the mass and the spin. Black holes are simple objects, so there's only mass and spin that describes. And the Kerr geometry is basically geometry that depends on the mass and spin. So if we are able to measure the resonances of these modes and the duration of this of the decay of these modes, then we can test whether this frequency and duration fits to the prediction from Kerr geometry or not. This is an independent test to see whether we detected a black hole with Kerr geometry. And there is an ongoing. This event has a very strong signal to noise ratio of 24. This is the strongest signal that we have ever detected, the very first and the strongest. And there's an ongoing debate whether we detected these resonances, these quasi-monormal modes that are decaying or not. And there's also debate whether we detected more of these harmonics. So it's something that is yet not crystal clear. And here I want to show of approach from our model independent searches. So I show here the time frequency evolution of the signal from the discovery paper, and then on the right our latest time frequency high resolution transformation that tells us how the signal is evolving in time and in frequency. So we can track, you can see that we can track many more details, and there is indeed an excess energy around 230 hertz, where people say that where people claim that they detected quasi-normal modes. And now this is the question on how significant it is. So this is so I hope this also answers the question of testing the geometry of the final black hole, of the Kerr geometry. Okay, so let me now go to the second event, the GW 190521. This is the very first detection of intermediate mass black hole. And what does it mean, intermediate mass? From stellar evolution, the black holes can be created up to around 100 solar mass.
Or actually, if I could still go back to that previous slide. So what about those quasi-normal modes? Do we control what we measure, or we just only think we measure those quasi-normal modes?
So this is a difficult question, because even if we see something, what is the statistical significance of that? And yeah, this is like different methods have different ways of assessing that. We want to say that we detected with like 3 sigma confidence, meaning that probability that we make a mistake is like less 0.1%. But yeah, that's yeah, like we want, they're like assuring that the significance is actually a very difficult problem.
Thank you.
So intermediate mass black holes are between the stellar mass below 100 and then above 1 million solar masses for supermassive black holes in the center of galaxies. And the origin of such black holes is unknown. There are no actually confirmed detections from the electromagnetic observations. If we think this intermediate mass black hole, GW 190521, had a mass, the final black hole had a mass of 150 solar masses. So this is nicely above 100 limit. So this is the very first gravitational, the very first intermediate mass black hole. Then Graham et al. Observed certain signal that is incoincident to this black hole. So potentially we may have an electromagnetic counterpart to this measure. And
what is this electromagnetic counterpart? I mean, what do you expect? What frequency? What do
so
what you can say about this electromagnetic counterpart? What to expect from it?
So the theory is that if we have a supermassive black hole and a accretion disk around this supermassive black hole, there is a lot of matter inside that disk. There are binary systems that go around, and because of that matter, of that denser matter in that disk when there is a merger, or when the black holes is going through that, or maybe when the black hole is going through this environment and merges, then it excites some matter that is around. This is roughly the like potential theory.
I haven't understood the answer, sorry. But let me then rephrase my question. What frequency of electromagnetic radiation you expect?
Yeah, yeah, I don't know answer to this. I don't remember
Okay.
what they measure back then. Yes, I don't know this particular one. So this event came so unexpectedly by many that some people say that these black holes shouldn't exist, but there they are. However, many people basically don't read predictions and papers, and Belczynski et al. In 2009 predicted that such heavy black holes can exist and can emerge and can be detectable. So that's why I crossed out this the phrase here. Now, I was in charge of the online analysis that detected the very first. So we wrote a paper on how this event was detected with using minima assumptions. We described the procedure leading to this detection. In low latency, this event was detected with a false alarm rate of 1 per 28 years. But after we acquired the data, we looked at the noise sources. We mitigated the noise mainly in the low frequency. We were able to achieve a significance of 1 per almost 10,000 years, which tells us it's a confident detection. And we also performed waveform analysis to see whether our reconstruction is in agreement with the models, and it is. We don't have a chipping signature for this. This is a very short signal, so there is no chipping structure, only basically the ring down. So the final black hole that decays, and Heuristic localization agrees with the models, and the waveform is also in agreement. Then we also analyzed there was and there's still a lot of debates of the nature of this event, and we analyzed whether this is whether this is a collision of black holes with eccentric that have eccentric orbits, in short EBBHs, and we published a paper in Nature Astronomy on that. We found that this type of analysis is challenging because the precise model are not yet developed. So we had to use many models that are available at that time, and we found that the potential eccentricity could be 0.7 of this event. So then if we have such a big eccentricity, eccentricity is going from 0 to 1. So it's a highly eccentric system, with high elliptical orbits. So it can come from active galactic nuclei or globular cluster. When we have a lot of black holes, so the probability of having eccentric system is larger. Maybe there is some triple systems, we don't know, but it changes the paradigm. Then we also analyzed this event in terms of the instability mass gap. So one of the component masses, component of this merger lies in the per instability supernova mass gap. So there is a mechanism called per instability that above 40, 65, it's unknown what is the value or whether this mechanism is real. Above that mass of a star, if it explodes, it basically destroyed without leaving anything behind. So if we so there was a debate whether this heavy black hole is just a statistical fluctuation. We proved that that this event is actually an outlier of the population of the stellar black holes, that it cannot be explained by the statistical fluctuations, even assuming the limit of this per instability at the 65. And then if we exclude this event from our sample, then none of the other gravitational waves that we're detecting during O3 are above 50 solar mass gap. So this is one of the studies that we also did. And now let me transition to gravitational wave transient catalogs. So LIGO Virgo published few catalogs, and I was involved. I'm involved in many LIGO papers. So I'm involved with some of these catalogs. In the first catalog, 7 gravitational waves were reported. With the second catalog, 39 more events, and the third catalog at 35 more events. So total number is roughly 90, depending on how to count them. But it's around this is around 90 of gravitational waves that we detected. And in the last catalog, we had model-dependent match filtering pipelines, 3 of them, and then model-independent pipeline coherent waivers. Let me describe here the so-called CWB.
Could you return to the previous slide?
Sure.
What is on the horizontal axis?
On the horizon, it's basically there's basically no unit. It's the events. All these gravitational waves are displayed in such a way to have a nicely viewing picture.
Thanks.
So, because coherent waivers can detect gravitational wave sources that are unusual, like the first gravitational wave detection or intermediate mass black hole. In the catalog, we include 3 events that are potentially coming from unusual binary systems or from some other populations. And these are events with probability of being coming from the binary black hole population of more than 50%, with false alarm rate smaller than 2 per year. And all of them don't really show the regular chipping structure coming from the from the regular binary sources. And for all of them, there was some glitch associated. So it's unclear whether they are coming from a certain other population or they're related to detector noise. Now, let me go to the future, even to the far future, and relate the field of our gravitational wave astronomy to particle physics. So a century ago, we had electron, proton, neutron, and then like we had to wait quite a long time before we had the whole zoo, like many different species of elementary particles. And potentially it can be the similar situation for us when we have compact objects such as black holes or neutron stars. And then maybe in the future we will discover a zoo of astrophysical compact objects that currently many of them predicted theoretically, but not yet observed. Also, in other paraphrasing how we can measure what is the structure of elementary particles. In order to understand the inner structure of elementary particles, we need to smash them. So we need huge colliders to do it. And the situation can be similar for the compact objects, that in order to understand their inner structure, we need also to smash them. It's fairly clear. It's fairly clear for binary neutron stars when we can learn what is the structure of what is the equational state of ultra dense matter, and this is what we are hoping for. Understand the structure of the neutron stars. Could be maybe we will be able to learn about the inner structure of black holes. So this is something for the future, or maybe even far future. So let me switch gears to a potential source that could be one of the most interesting events of our century. So people are observing sky from the time when they have eyes and they looked at the sky, and they could see stars, but from time to time a new star appeared on the sky, and back then they didn't know what is that, but now we know that these are exploding stars, and the rate of these events is 1 or 2 per century, but in our own galaxy. But the last one was 300 years ago. The Chinese observed one in 1054, 1 millennia ago, and right now we see exactly the remnant of this explosion, and we know that they were writing exactly about this event. So how does it work? When a massive star is burning its fuel, it creates heavier and heavier elements, starting from hydrogen to helium, through oxygen, up to iron. And the burning stops at iron. Iron goes into the center, creating an iron core. And when the core exceeds Chandrasekhar mass of 1.4, 1.5, so mass of our sun, then it collapses under its own weight. So you can think of an iron core of 1,000, 2,000 kilometers to a nucleus core of a radius of around 50 kilometers. When we calculate energy available, it is roughly 0.15 solar mass, 15% of a solar mass. And then what astronomers observe is only 1% of that energy. So 99% of the explosion energy actually escapes with neutrinos. So we have the process of colliding protons with electrons, creating neutrons and neutrinos that interact with matter super weakly, and they basically fly away. These core collapse supernovae are extremely challenging to model. All the fundamental forces are relevant to create an explosion, and there's a lot of unknowns in the modeling. And and detecting of gravitational waves can potentially teach us some fundamental questions like nuclear equation of state, quantum chronodynamics phase transition. If we have black hole creation, then we can potentially measure the creation of an event horizon. We can also, together with gravitational wave and neutrinos, we can measure the neutrino mass. Now, these are great multi-messenger events. We have neutrinos, we have gravitational waves, we have electromagnetic waves, and they are coming in different stages. At the moment of the explosion, we have a huge outflow of neutrinos, and then several orders of magnitude, we have gravitational waves. So let me focus on, and the electromagnetic signal is coming way later after a shock that blows up the star reaches the surface. So what are the energy of gravitational waves from exploding star? I have these are extreme, as I said, these are extremely challenging to model, and there's a lot of uncertainties in physics in the predictions. So I took all the models that are available, all the models of gravitational waves, and then I analyzed them. This is one of the plots from my work. The typical frequency of this explosion is pretty high, around 800, 1000 hertz. The energy range is 10 to minus 10, 10 to minus 7 over solar mass. And this is a few orders of magnitude from a typical explosion energy of a supernova. Current constraints from gravitational wave observation are still also few orders of magnitude higher than the gravitational waves, than the energies predicted from the multi-dimensional simulations. Now, currently we are going through a search, and I'm showing preliminary results. If we believe in the neutrino, there are few explosion mechanisms, and the most believed is that neutrinos leaving the star interact with the star, creating, like, hitting the star from inside, creating an explosion. And this is called a neutrino-driven mechanism. And this type of explosions we can see up to around 13, 14 kiloparsecs. As a point of reference, the galactic center is at the distance of around 8 kiloparsecs. So we are slightly going beyond our own galactic center. When we have magnetorotational driven explosions, the situation is a little bit better. We are going up to 16 kiloparsecs, so twice the distance to the center of Milky Way. For the quantum chronodynamics phase transition, we found that it's like 2 kiloparsecs, so very nearby. And these are also like challenging waveforms to detect. For black hole emission for this particular model is like 1 kiloparsec. So some of the models are still, there's a lot of uncertainties in these models, and here we are using those that are coming from the state-of-the-art simulations. But because we don't know what is happening in the center of a star, we also use extreme emission models that are going that are detected, the emission from this extreme emission go up to several megaparsecs, so like far beyond Milky Way. And we found that the limits, we do like more precise analysis of what is possible, and in the paper we'll describe many different other results, but this is one of them. In the low frequency, if the gravitational wave emission is in the low frequency, then around 10 to minus 4 of solar mass is the limit that of the emission. And in the high frequencies, the situation is still not as interesting. So let me go to the last slide before the summary. I'm also performing other searches, like this generic search where we look for all possible gravitational wave morphologies, where we are not constrained to any gravitational wave source. So core collapse supernovae, neutron star glitches, cosmic strings, unknown, binary systems, and these type of searches are performed regularly by LIGO and Virgo. Here we reanalyze the data with improved algorithms, and we improve our sensitivity. We detect more gravitational wave sources, but beside binary systems, we have detected any new gravitational wave source. So this is still something to we hope in the future. So as a summary, the dynamical universe is one of the priorities in astronomy and astrophysics. The gravitational waves, together with other messengers, are great probes to study fundamental physics and explore the universe, finding the equation of state of ultra-dense matter, QCD phase transition, testing general relativity, finding neutrino mass, explore learning about explosions of stars, exploring active galactic nuclei, and so on. The list is long. In March, we'll start the observation, and we'll have detection every day. It's a great opportunity for the discovery, and model independent searches already shown that because of the flexibility, they can be suitable to detect unexpected sources and phenomena. And we hope we will have surprises in 04. So thank you very much.
Thank you. Thank you for your talk. Now there is time for questions. There were a lot of questions during the presentation, but perhaps there are also.
But is the time also for comments?
Yes.
So from the presentation, I remember many things, but one thing which surprised me that you said the following: you expect discoveries of unexpected objects. This was some, I would say.
Yeah. So
something.
it's like naming. So for the unexpected, I mean basically, those sources with exceptional.
So we expect discoveries of unexpected astrophysical sources.
Yeah. Mm-hmm.
Other questions or comments?
I have one question which continues the previous question, more specifically. If this unexpected source can be described using this coherent wave burst approach, then I understand how you do that. On the other hand, if it is a stochastic signal, then how can you tell a stochastic signal against stochastic background? Looks to me quite hopeless. Could you comment?
So that's when we need two or more detectors. If we have one detector only, then yeah, this is hopeless. It's like almost impossible to say that we see a signal with the stochastic morphology. But if we see a similar pattern in two detectors, then the confidence grows, and
Two messengers.
If we have a messenger, an additional messenger, that the significance grows even more. First, if we have only gravitational waves, we have two detectors, and we compare the signals between two detectors.
Okay, thank you.
Are there more questions? Maybe I ask a question. So in what way theoretical relativists could help you in your work? What can we contribute?
The first thing that comes to my mind is understanding the generation of gravitational waves, whether there are some deviations or like looking for the deviation from general relativity. If we observe for like here quasi-normal modes, does it agree with the models? If we have some quantum effects, do we observe them in the data? So here we are as agnostic as possible. So we humbly look at the data, and we look where we see signal, and then we calculate the significance of that, and then if it is not agreeing with the models, then yeah, maybe we need some other models. And even for the regular binary systems, there are different models. There are a lot of models describing just the evolution in time and time evolution of a signal. And if we have precise measurements, not all of them agree with each other. Some of them have higher harmonics. Some of them have precession. So like many secondary effects were that are hard to compare. So in terms of like even calculating the waveforms, like simple calculation of the waveforms, there's a lot of theory involved, a lot of approximations, and choosing the coordinate systems even. Yeah, there's just for creating the waveforms for binary systems. There's a lot of theory involved. Basically, solving Einstein equations.
Yeah, thank you.
Okay, I have a question. Actually, two questions. So first of them, you said that after the improved sensitivity, it will be possible to detect on average one event per day. And on the other hand, the signal you have at the detector for the same source, it would change as 1 over the distance from the source. So if you detect one event per day, then there should be plenty of events which are just below the threshold. And so the question is, in the noise of from the measurement, what part of this noise is Earth-based events, like cars moving, earthquakes, these kind of things, and what part of them are gravitational waves emitted by sources which are just below the threshold, where there should be many of them?
Yes, I don't have a good plot explaining that, but you can think of it as number of detected sources grows like a cube over the volume, so like of the distance. So this is like goes like like um, like a cube. But for the noise, the situation is different, and the noise grows exponentially. So at for the very weak events, we have many more noise than actual gravitational waves. It's like if you have a Gaussian noise, then the growth is exponential.
Okay, let's say that there is some threshold. If it's exceeded, then we classify it as an event, and then we have something which is just 2 times farther apart. Then there will be 8 times more of these sources which are 2 times smaller, which means they are just below the threshold. And so it will be there will be not 1 event per day, but there will be 8 events per day. Below the threshold. So they
probably the contribution to the noise is negligible. There's noise anyway.
Probably. And the second question is how is the access to the data organized? Are they publicly available, or you need to be within the collaboration to have access to the readings from the instruments?
Okay, so yeah, coming back for the first one, maybe this is a good I'll try to explain here in this sense. This is the noise, and the scale is in factors of 10. And if we have the distribution of the gravitational waves, they roughly go with a much with less steeper slope. So you can imagine gravitational waves that are the distribution of gravitational waves going above the noise and then going under. So this is roughly the distributions in terms of like a SNR. So this is for the first question, and for the second, availability of the data. At the moment, all of the data is public. However, when the O4 starts, then I think one has to wait 1 year or 1 year and a half. I don't know exactly what is the number right now, for the data to be shared publicly. So it's because I'm in the collaboration, I have access to the data basically every second when they arrive. But for people outside collaboration, one has to wait a long time.
Thank you.
One more question. You, at one of your transparencies, it was written that instead of solving the Einstein equations, we let the nature solve them. But what if those equations are not exactly true? Then what do we do?
Yeah, but then so we will measure something, and then probably we'll have to modify the equations to fit to the data. Maybe there are some effects that we don't observe right now, but we'll detect them. We'll observe them. So far, like everything agrees with the Einstein equation, but there's a lot of work toward understanding the deviations from general relativity, from Einstein Equation. We constrain it more and more, but eventually we might see something that doesn't fit to these equations. Then we'll try to fit basically to what we observe.
Thank you for your talk, and thank you for answering our questions, and thank everybody for asking the questions, and let us clap once again.
Thank you.